Lab 3. The purpose of this lab was to use computational models to find the mass of the black hole, modeling the net force of gravity between a star and a black hole. Part 2 was to find the initial velocity for a spaceship to fly around the black hole without crashing on the planet or the black hole, using a similar computational model. The preview of the main result was that the mass of the black hole was 1.37 times 10 to the 34th kilograms, and the initial velocity was this number in meters per second. These are the key concepts that were based on Newton's second law, which is net force equals change in momentum over change in time, which equivalated the velocity update formula and position update formula. Some key concepts was the net force was separated into the parallel component in the direction of motion, which changes the magnitude of momentum, and the perpendicular component, which is orthogonal to the direction of motion, which changes the direction of motion. The gravitational force was based on Newton's third law, which basically states that for every force there's an equal and opposite force. So in the equation there's mass 1 and mass 2, and then vector r is pointing from the source to the system. The gravitational force points from the system to the source because the system is attracted to the source. So this was the model representation of the forces. So this was part 1, where the black hole and star had gravitational force on each other. The system was the star and the surroundings were black hole and everything else. This was part 2, where the spaceship and the black hole and the star all had gravitational forces. The systems were the star and the planet, and the surroundings were the black hole and everything else. So these were the initial conditions for part 1. These were the equations to code. Translated into code. So for the net force, the parallel component of the net force, the perpendicular component of the net force, and the mass of the black hole. And that's how it was calculated. These were the iterations in part 1 used to calculate the velocity and momentum and net force. And the result was the magnitude of the net force was 0.04733369 newtons. These were all in newtons, the F-net parallel and F-net perpendicular, and then the mass of the black hole was calculated to be this value through the average of the multiple mass values given. So this was the computational model for part 1 predicted an elliptical orbit around the black hole due to the force of gravity. So when the star was further away, it was slower since there was less gravitational force, and when it was closer to the black hole, it was faster since there was a larger gravitational force. So the changes in the parallel component of the net force changed the magnitude of momentum, so basically it increased in speed when close to the black hole, and then the changes in perpendicular changed the direction. Possible sources of error included rounding in the gravitational constant and iterations, which probably caused the multiple values of the mass of the black hole. So these are the initial conditions for part 2 in the code, which was used to find the initial velocity. These were the equations to code with the r vectors for the black hole, ship, and planet. And then these were the iterations in code. The result of part 2 was the initial velocity of the spaceship here, and the shortest distance between the spaceship and the black hole was given here, which means that it had the strongest gravitational force at that point. So the initial velocity was determined to be this in meters per second, which means the spaceship moved to the left more than upwards, and negative x direction more than like the positive y direction. At its shortest distance between the ship and the black hole, this was the value, it experienced a maximum gravitational force. So the spaceship reaches escape velocity due to maximum gravitational force, which allows it to leave the orbit of the black hole, as demonstrated in the previous slide. And the speed increases greater than the escape velocity for it to escape. So the possible sources of error include rounded values. So how does net force and its parallel and perpendicular components differ from the rate of change of momentum and its parallel and perpendicular components? So we set F-net equal to dp over dt in our code due to Newton's second law, but they differ in calculation. So F-net requires the mass of the black hole, while dp over dt is calculated through position, velocity, and momentum in time. So if you want to enter the orbit of the black hole, what initial velocity would you need? I did this experimentally in the code, and I calculated its initial velocity here is negative 1.6 times 10 to the 6th in the x direction, and 1.0 times 10 to the 7th in the y direction. So I decreased the magnitude of the x component of velocity by a lot, and also decreased the magnitude of y component of velocity a little, which allowed the trajectory to go towards the black hole. Thank you.